continue our discussion of rotational motion. In the last lecture, we saw the relation between the angular velocity and angular momentum, and we sort of learned that there is a strange fact that angular momentum and angular velocity need not be in the same direction. So, this is very different from the situation in the case of translational motion, where the linear momentum p is equal to m times v is always in the same direction as the linear velocity v. Today, our goal is to examine the cause of rotation. So, when we discussed Newton's law of motion week 2, so we said that the cause of motion is the force. So, that was a confusion for a long time among people, that what is the origin of motion. Sometimes people thought that the origin of motion is the change in position. So, the velocity is, if you have a velocity, that means that is the cause of. So, the force is some external agent that causes the some object to move, and for long time people had this misconception that force causes change in the position, that is velocity. But later, when the Newton's after Newton's law of motion, by the research of Galileo, Newton, etc., it is now clear that force does not, that is the interaction between our system with its surrounding, causes acceleration, that is change in velocity, not change in position. Now, today our goal is to look at what is the analogous situation for the rotation, what causes rotation. Now, this we have implicitly we know that what causes rotation is the torque. So, that is another consequence of force. So, force on a, so if we take a system and the system, so it is interacting with its surrounding. So, there are some these interactions are the forces, and this can cause our system to translate, but another consequence of the force is the rotation. It can also cause our system to rotate. So, this is why we not only need to mention the magnitude and direction of the forces acting, but also the line of action of the force. So, this is what we learned when we learned how to draw the free body diagram correctly, that you need to specify the line of action also, because the force can also cause rotation. So, today is our goal is to examine the relation between force and its rotating effect, which is expressed by torque. So, what is the relation between angular momentum and torque? So, you know from your high school physics that the two things, that this torque is expressed as, the definition of torque is that this is the moment of force and this is expressed as a cross product. So, let us say that we consider a single point mass and with respect to some particular origin, and this origin is fixed in space, and this is our coordinate system. So, this vector r is the position vector of this point mass, and let us say some force is acting, let us say in this direction. Then, so this is the line of action of the force. Then the torque due to this force about this point, pivot point origin of, that is the origin, is given by this definition r cross f. And you have also seen that this causes the effect of this force is to change the angular momentum, which is analogous to the Newton's law, that the cause of force is to change is equal to the rate of change of linear momentum. So, our goal is today to critically examine this relation. So, remember that this relation we also used implicitly when we talked about the statics problems, when the objects are motionless, and we use this torque balance condition as a one of the essential criteria for statics or mechanical equilibrium. In that case, we use this definition always, that tau is r cross f. Today, we are going to see the relation between the angular momentum and the torque, and specifically we want to discuss this question, that under what condition torque is equal to r cross f. So, when I say torque, I mean that some external agent that causing a change in the angular momentum. So, let us work it out in some detail. So, let us say that we start with our definition, that for a point mass, the angular momentum of this particle of mass m is given by r cross p. So, then if we look at the rate of change of angular momentum, that will be the rate of change of this quantity. Then it has two terms. So, I can apply the chain rule of taking derivatives. So, this will be now this is v and this is m v. So, the first term is basically a cross product of velocity with respect to itself apart from the mass. So, that means this is 0 by definition of the cross product. Hence, we have the dl dt which is equal to r cross dp dt, which is the force as listed here. So, this is how we get this relation for a single point mass. Now, before proceeding further, let me discuss a very interesting and very important consequence of this particular case of a point mass. So, we are talking about the central force motion, that is, a particle is subjected to a central force. What is a central force? It is a force such that if this is the particle, so let us say some particle is moving around the origin, and there is a force acting on this particle which is along its position vector always. So, this is the direction of the central force is along the position vector. So, this is the definition of a central force, that is why it is called central. Now, it can be towards the origin or it can be away from the origin. So, the Fr can be positive or negative, the magnitude of the force, but the direction is always along the position vector. So, if this is the case, then we can immediately see that a particle of moving in such condition will have a constant angular momentum. Why? Because if what we find is r cross f, and so we find that dl dt is equal to r cross f. Now, if f is along the direction of the position vector, then this is 0. So, then if f is proportional to r, then dl dt is 0. That means that L is conserved, that is, the particle's angular momentum is a constant, and geometrically if the angular momentum is constant, that the only way it is possible if the particle is moving in a plane which is perpendicular to the direction of the angular momentum. That is the only way the angular momentum can remain constant. You can check that. So, here is a very important application of these simple concepts. So, we take this example of Kepler's laws of planetary motion. Using just this simple definition, we can understand Kepler's laws of planetary motion. So, let us start with Kepler's second law. So, what does it say? So, basically in this case the origin is could be a massive particle such as sun, and this particle that is moving around the origin is, let us say, our earth or any planet. So, the Kepler's second law says that a line segment, so here there is a line segment. So, the violet line joining the particle and the center, that is the sun, sweeps out equal areas during equal intervals of time. So, this is the blue shaded region. So, notice that the particle is not moving with a constant speed. Sometimes it is moving fast, sometimes it is moving slow, and you can see that the blue, if you follow the blue shaded triangle, sometimes it becomes wider, sometimes it is narrower. Why? Because this is showing that for equal amount of time, if the speed is higher, then it will cover more angular arc. So, the blue shaded region will appear wider, whereas if the speed is small, then the arc length will be narrow and the triangle will appear narrower. But Kepler's law says that the area of this triangle of the blue shaded region for equal amount of time delta t is always the same. So, let us derive this, it is very easy to derive this. So, the blue shaded region, blue shaded triangle, so let us draw some particular instant. Let us say it makes an angle. So, this is our sun and this is at the earth's position at t, and this is the earth's position at t plus delta t, and this angle is delta theta. Then the arc length, this arc length is r times, so r, which is, so in general the distance between sun and earth are different. So, the r, which is the distance between sun and earth, is a function of theta. And now you can, if delta theta is very small, then we can approximate this piece of the this arc as a straight line, so that this is approximately a triangle. So, you can use the formula for the area of a triangle, half into base into height. So, this is base and this is height, and so this is r, and you get the half times r, and d theta, if the speed, angular speed is omega, then the angle covered delta theta is, so this is your delta theta will be omega times time interval dt. So, then if we take the rate of change, then dA dt will be half times r omega, and r omega is the tangential speed of the earth along the trajectory. So, this is half times r v, and if I apply this definition L equal to r cross p, which is r cross m v, then we see that the magnitude of L is m v r. That means r times v is L by m. So, our dA dt will be, and there is a factor of half sitting before that, is L over 2 m. Now, m, which is the mass of the earth, is constant. We can assume, let us assume that this is constant. So, if this is constant, then we find that this dA L is also constant, we just proved. That means dA dt is equal to a constant. So, this is basically the content of Kepler's second law. I also mentioned the nature of the trajectory. So, Kepler's first law. So, the first law says that the orbit of a planet is an ellipse with the sun at one of the two foci. Now, what from this simple analysis of the conservation of momentum, we can only say that the sun must move in the same plane. So, in general it could have some complicated trajectory, but no, it always moves in the same plane. So, this is consistent with Kepler's first law, because ellipse is an orbit in a plane. So, it basically shows that the center of the sun is always in a same plane. Now, we cannot, from this analysis, we can only say that the orbit is planar. So, Kepler's first law contains more information. It in fact says that the orbit is ellipse. So, this is true only for a special case where the force law is inverse square in r. So, note that here we just mentioned that this is some function of r. So, when I say some function of r and it is directed, we just assume that this force between sun and earth is directed along the line joining sun and earth, but we do not know what is the magnitude. So, once we know the magnitude, then like using these Newton's laws of universal gravitation, then Newton was able to prove that the law this orbit, the planar motion is in fact an ellipse. So, let us come back to our discussion of under what condition we the torque, that is dl dt, is equal to. So, this I mean the change in rate of change in angular momentum is equal to r cross f. So, now we have, so we consider a single point mass. Now, we generalize it to an extended object. So, let us for simplicity we describe this extended object as a collection of point mass. So, the first case that we consider will be where our origin is again fixed. So, like before, this is our origin and this origin is fixed, and there are sort of point mass, and for concreteness we have 4 point mass. Now, in this case we have to calculate the dl dt. So, let us work it out. So, in this case L, the total angular momentum, so you can compute it for each of these particle. So, for particle I, position is r I and its momentum is p I, and then you have to take a sum over all particles. Then the rate of change of angular momentum is equal to, again I can take the for each of the particle I can calculate and then add it. Now, this one as before will be dr dt cross pi plus ri cross dpi dt. As before, this term will always be 0, because pi is mi times pi. So, this term is always 0. So, we have just so far seems like it is the same algebra as the case of single point mass. Here is the difference. So, for a when we have a extended object, then suppose when we write down this the force on particle I, so we make a distinction between two kinds of force. So, let us say this is our system. So, this is our system and everything else is surrounding. So, then there will be interaction between the surrounding and the particles inside the system. So, from surrounding, interactions surrounding from and system, but each particle of the system can also have force from other particles. Particles or parts of the system. So, we call this as external force or external interaction, and this one as internal force or internal interaction. So, then our Newton's law will be the total force. So, this is total force on particle I. So, this will be as an external component and an internal component. The origins are different. The external component is coming from outside the surrounding, and internal component comes from the other particles in the system. So, let us say if I take this particle, then the force due to R1, R3 and R4 constitutes the internal force on particle 2. So, we write it as if external I plus sum over I Ri cross F internal I. Now, here is a take home exercise that show that in this situation where Fi internal is the force due to all other particles, show that this term vanishes. So, if you add the for each of the, so what I mean is that for each particle this term is non-zero, but when you add this term for, so if you calculate for R1 cross F1 internal will be non-zero, for R2 will be non-zero, R3 will be non-zero, R4 will be non-zero, but if you add this term for, so let us call that tau 1 internal, tau represents torque. So, tau 1 internal plus tau 2 internal plus tau 3 internal plus tau 4 internal will be 0. This is a consequence of Newton's third law. So, it is easy to show because, so I will give a hint. So, the force on 1 by 2, so this is on 1 by 2 is equal to minus force on 2 by 1. So, it is a consequence of this fact. So, you take this and work it out in detail yourself and convince yourself that this term going to be 0. So, this is 0. So, then our dl dt is going to be sum over I Ri cross Fi external only. So, that means that sum over I tau I external. So, if we take an object like this, I just what I showed is that all the internal force, the torque, if you sum over all the forces, the torque due to all the internal forces will be 0. So, the only force that matters are the forces that are coming from the surrounding. And if you recall the problems that we did, the examples that we did, so when we talked about the torque on an object, it was always the torque coming from the surrounding. For example, if I look at the torque due to Earth's interaction, so that is a force. If this is our system, then the what causes the rotation is an external force like the gravitational attraction due to Earth, which is coming from the surrounding. So, this is true even for an external force. But here comes the third case and the most interesting case. So, in this case what we have is we now consider our frame which is moving, and when I say moving, so far in the two situations that we considered, the frames where, that is our origin, was fixed in space. So, these are what is called inertial frames, that is we assume that in frames, these frames, the Newton's second law is valid, which means that, I mean, in this is a frame in which Newton's first law holds, that is if there is no other external interaction, then the particles will move with a constant velocity. But now let us assume that our origin itself is moving with respect to some inertial frame. So, and when I say moving, it can have move with constant velocity or it can have some acceleration, it can be an accelerating frame. So, this is a very interesting situation which we did not discuss more like earlier in our course, and this is the only situation in which we will briefly mention this. But so, this is this non-inertial or accelerating frame of reference, and suppose if the question is, if we take such kind of reference where the origin itself is moving, then can we write down the torque is equal to R cross F. So, this is an interesting case. Now, because we cannot write, it is not guaranteed that in that frame the Newton's law will Newton's laws of motion will hold. So, we need a second frame which is fixed, an inertial frame. So, this is the frame which we will call the lap frame. So, consider that this is the origin of the lap frame, and this is the R naught is the origin that is moving. The position of the origin in the lap frame is R naught, and in the lap frame the position of all the particles. So, we have only two particles in this particular example is R1 and R2. Now, the position vector of the same particles with respect to this moving frame. So, this is the moving frame, is R1 minus R naught and R2 minus R naught. So, we want to calculate that what is the rate of change of angular momentum of this system of two particles in the moving frame. So, the first term is Ri minus R0, this is the position with respect to the moving frame, times the momentum with respect to, so this is the momentum with respect to the moving frame of particle I in moving frame. So, we have to calculate the time derivative, and as before we get two terms. The first term will be the velocity times momentum in the moving frame. So, it is 0, and the second term is the interesting term, which is the position of the particle I in the moving frame times the derivative of the momentum, and the derivative of the momentum now has two terms. The first, so this is the acceleration. So, this quantity r I double dot minus r I r double r 0 double dot is the acceleration of I in moving frame. So, this is the acceleration of the particle 1 in the moving frame, and r, let us say r 1 dot dot is the acceleration. So, r I dot dot is the acceleration of I in the lap frame, which is the fixed frame. This is the difference. Now, let us work out these terms. As before, the m in the Newton's law says the mi times the acceleration is equal to the total force on particle I. This note that you can write only in the fixed frame, it is guaranteed only in the fixed frame. There is no way you can, it is guaranteed if the frame is moving. If the frame is accelerating, it is definitely not true. Then, as before, we can divide it into, so note that this is the real physical interaction which obeys the Newton's third law. So, we divide as before into external force and internal force. So, in this particular example, the force on 1 by 2 is the internal force and everything else is in the surrounding. So, this is our system, everything else is in the surrounding. So, those will be external force. The first term then will be cross F external plus internal, and the last term will be sum over I r I minus r 0 cross mi times the acceleration of the frame itself. So, I am writing all the equation with respect to the fixed frame. As before, you can show, so this is what I have written down. Now, as before, you can show that the first term is so this is the sum over I all the external torque. The second term with the same argument you can show by applying Newton's third law, this is going to be 0. Now, the last term, so the last term is now, if I take this first term, so the first term will be and in the second term we have just sum over mi times r 0 cross dot dot. So, in this case this one, if I recall the center of mass definition, so this is nothing but the total mass of the system times the position of the center of mass, and the second term is nothing but the total mass of the system times r naught cross so this is a minus sign. So, this is what is written in a neat way here. So, we see that the dLdt is not only the tau external as before, but has some extra term, and only if this extra term is 0, then we get this relation that the dLdt is equal to r cross f. So, this is the r cross f term. So, under what condition the second term is 0? So, you see from looking at this second term that if this is the center of mass position. So, if the moving point is the center of mass, that is the origin is the center of mass, then this term is 0, that is r equal to r naught. Or if this acceleration is 0, then also this term is 0, that the origin is moving, is not, can be center of mass, can be different, but it is moving with a constant velocity, not accelerating with respect to the fixed frame. Or this is the origin is different from center of mass and is also accelerating, but for some reason this difference is the parallel to the acceleration. So, this is a very special and strange condition. If one of these three conditions satisfies, then we see that this term can be 0. In that case, the cross product itself will be 0, and we end up with the relation that the rate of change of angular momentum is equal to the rate of the total external torque, that is r cross f. So, this is something that is usually not highlighted in textbooks. So, I just wanted to mention it. So, to summarize, if you take a inertial frame, then we looked at the relation between the rate of change of angular momentum and torque. We found that in an inertial frame, the rate of change of angular momentum is equal to r cross f. But if we take a moving frame of reference, it is not true in general, and we discuss the conditions under which it is true. Thank you.